Absolutely. Thank you very much, Daniel, for your kind words of introduction. Welcome, ladies and gentlemen. My name is Detlef, and together with my colleague Jare, we will discuss topics and tips and tricks for improved results in high-performance anion exchange chromatography with pulse temperature detection, short HPAEC-PAD. And here's the agenda of today's presentation. We will begin with a brief introduction, a very brief introduction, then address the water quality question, followed by a discussion on eluent degassing and preparation, as well as cell and waveform topics. And finally, there will be a section on calibration. Let's get started and jump right into the introduction. Ladies and gentlemen, this is the third installment of our annual webinar series, so please allow me to pick up where we left off last time. We discussed the prerequisites of reliable and reproducible carbohydrate analysis using HPAEC-PAD. We concluded that the key prerequisite is a dedicated carbohydrate analyzer for isocratic and gradient separations, like the Alexis carbohydrate analyzer shown on this slide. It is this combination of specialized, dedicated, and optimized hardware with the state-of-the-art column family called SweetSep that provides us with the greatest flexibility, high selectivity, and sensitivity. This is essential for meeting the demanding needs of carbohydrate analysis. I promised to deliver a short and crisp introduction, and I think it was. Now, what else do we have to consider when running HPAEC-PAD? Please allow us to dive into the question about water quality. A blank page. So people who know me well are aware that I have a favorite phrase when talking about water quality in the laboratory. I often say this: good water, good results; bad water, bad results. Let me repeat that because it is important. Good water, good results; bad water, bad results. Now, you might have laughed about the pictures of superheroes and supervillains, which I intentionally created with the help of AI, because deionized water is still one of the most underrated and undervalued chemicals in our laboratories. Your laboratory's DI water system should be regarded as an asset, carefully protected and properly maintained, since it produces this highly valuable chemical called DI water. Have you ever thought about DI water as a chemical? If you start thinking about that as a chemical, it changes everything. Here we summarize on this slide, we summarize the minimum requirements for DI water. It should have a resistivity above 18 megaohm, addressing ionic contamination, and it should have a TOC below 10 micrograms per liter, addressing the dissolved organic matter. Consider this IASTM type water specification as minimum requirements. Why? Because modern DI water systems will provide water with higher resistance and lower TOC. There's only one crucial guideline. These numbers should not drift. If they do, it means your DI water system needs maintenance. Good water, you get it. So please keep an eye on your DI water system and consider DI water as a chemical. It really helps. Jare, why don't you take us through the next steps?
So now that we've laid the foundation for a good eluent, let's talk about how to deal with enemy number one of a good eluent. What is enemy number one? Carbon dioxide. So why did I describe CO2 as the main enemy of an HPLC-PAD eluent? It's because CO2 has a high solubility in DI water. If you leave the water exposed to the atmosphere, CO2 will quickly dissolve. And this process is accelerated when you stir it. Within the first minute, a large amount of CO2 will dissolve, as indicated by the resistivity drop. You can see how sharply it decreases. If you're not careful, the DI water can become saturated with CO2, reaching up to 55 millimoles per liter. Since carbonates, formed at pH of a typical HPLC-PAD eluent, has strong elution power, its presence will change the properties of the eluent. This results in a shorter retention time, varying sensitivity, and even differences in the selectivity. Therefore, we must prevent carbon dioxide from entering the eluent. To emphasize the last statement, I will show two chromatograms. The blue one shows the separation of halogenated carbohydrates with the mobile phase properly prepared and protected from the environment. The red trace, however, shows the same instrument, same column, same eluent, same operator. But we intentionally opened the bottle and allowed the CO2 from the atmosphere to be absorbed. Just compare the two chromatograms. You can see the dramatic difference. Not only do the retention times vary, but sensitivity, selectivity, and resolution do as well. This demonstrates the effect of the contamination we described, carbonate. And the best way to protect the element from the surrounding atmosphere is to use an inert gas. We use nitrogen. You can use nitrogen for sparging the eluent, displacing the dissolved gases with nitrogen. On our slide, both bottles are being sparged. If we close the vent of the right bottle as shown now, the space above the eluent becomes filled with inert gas. There are two terms used for this approach, to head pressure or to blanket the eluent. With sparging and head pressure, we protect the eluent from the surrounding atmosphere. When sparging, we even degas the water or the eluent with an inert gas. That is the easiest way to protect the eluent from enemy number one, CO2, and consequently, carbonate. So now that we have identified enemy number one and understood how to protect the eluent and avoid the uptake of carbon dioxide, let's discuss the tools available to implement what we just theoretically described. Let's talk about the eluent tray. So now, what is the eluent tray ET210? It's a module designed to hold 4 2-liter bottles for preparing high-purity sodium hydroxide containing eluents, allowing sparging and blanketing. When we talk about an inert gas, we mean nitrogen for two reasons. A, it works, and B, it's cheaper than helium. We will show you how to use nitrogen for this. We have a short video which we will show you in a minute. But first, since the ET210 is called a module, let's look at its installation and use. Installing the ET210 is straightforward. Simply place on top of another module to integrate it with the Alexis leakage management system and connect it to the nitrogen supply. However, the bottles, to be precise, the bottle assembly, requires our attention. Remember, for carbohydrate analysis, we use sodium hydroxide-based solutions in mol per liter range. This rules out glass as a bottle material because caustic solutions corrode it, releasing silicate and borate, which could contaminate the chromatographic system. Therefore, we recommend polymer bottles, such as polypropylene bottles shown on this slide. The specific bottle assembly, including the gas lines and especially the quick connectors, allows you to sparge and blanket the eluent with nitrogen. After working with them, I would even call them quick safe connectors. Why? Because when unplugged, they automatically seal the gas and the liquid lines. This means you can pressurize the bottles, disconnect the fittings, and there will be no spill. If there is no spill, lab safety improves. This is accomplished while avoiding carbonate and borate contamination, a real win-win scenario. So now it's time to talk about eluent preparation and how to handle elements and reagents. Let's start with preparing sodium hydroxide eluents. As the saying, a picture is worth 1,000 words suggest, we created a video on this topic.
How to use the ET210 eluent tray. We need a stir bar, a magnetic stirrer, a dedicated bottle and cap, a pipette, and of course the carbonate-free 50% sodium hydroxide solution. We start with drawing some ultra-pure water without splashing and pouring it gently into the bottle. Then add the magnetic stir bar and close the bottle with a cap. The red gas line is not needed now, so we can remove it. The next step is to place the bottle in ultrasonic bath for 15 minutes. Place the bottle with water on a magnetic stirrer, and the water is degassed further by sparging it with nitrogen gas. Therefore, the sparge line is connected to the ET210 eluent tray, and the other end of the line is connected to the bottle. Make sure to open the vent. Have a look at the sparging speed and adjust if needed. 1 or 2 bubbles per second is sufficient. 15 minutes later, the bottle can be disconnected. Make sure to close the vent. The next step is to add the sodium hydroxide. Draw the solution from the middle, as there is the least amount of carbonates. Add the solution to the water and quickly close the cap again. And quickly close the bottle with sodium hydroxide too. Set the solution back on the stir plate, connect the sparge line and make sure to open the vent. 5 minutes later, the bottle can be disconnected and closed. It will now require ultrasonic degassing one more time to remove the excess dissolved nitrogen gas from the solution. 15 minutes should suffice. Now the eluent is ready to be blanketed and pressurized with nitrogen gas. Connect the red gas line to the ET210 and regulate the gas flow down to 1 or 2 bubbles per second. Connect it to the cap and open the vent. After connecting the eluent to the system, it is ready for priming. For preparation of stronger eluents, a fast track is available. We start with drawing water, then add the sodium hydroxide with the vent closed. Stir the solution for 2 minutes. Then attach the red gas line to the cap to blanket the eluent. Make sure the vent is opened and connect the eluent to the system. It is ready for priming.
Let's proceed to making the sodium acetate eluent. Use high quality acetate and it should be pure white. This coloration indicates contamination, so do not use it. Adjust the amount of sodium acetate based on whether it's trihydrate or anhydrous. We use trihydrate in our headquarters R&D facility. We learned a trick from our users. Some prepare their sodium acetate by reacting glaciosidic acid with 50% sodium hydroxide, and then diluting it with water and mixing. We haven't yet developed an official SOP, but it should be straightforward, considering the degassing, blanketing, and safety precautions involved in an acid-base neutralization. It's quite clever and it helps avoid metal contamination. But let's stick with the standard process. Use degassed water to dissolve sodium acetate, then vacuum filter the solution to a 0.2 micrometer polymeric filter. These are commercially available polymer filters and only use one of those. Check the filter. If the filter cake is yellow, discard the sodium acetate. A yellowish filter cake suggests a possible metal contamination. After filtration, add the appropriate amount of 50% sodium hydroxide and store the final solution under an inert gas. Avoid heavy stirring and always maintain the nitrogen head pressure. And one important note, always prepare caustic sodium acetate solution. If prepared in water, the sodium acetate solution turns into a perfect breeding ground for bacteria. Nothing you want to have on your system, right, Detlef?
Absolutely right, Yada, absolutely right. Well, thank you very much. Which brings us back to our little lab book and the next bullet point, cell and waveform and polishing of the electrode. Now let's start with a couple of questions. Why do we have different waveforms? Why do we use different waveforms? Well, let's start with the outcome of using a waveform, regardless of whether it's a 3-potential or 4-potential waveform. Every time you cycle through a waveform, you lose a tiny little bit of gold. With some waveforms, you lose more gold than with others, leading to receding gold electrodes and consequently changing response factors. This means you need to keep an eye on the wear of the gold electrode, and here is one clear outcome from the very start. The waveform that results in the lowest wear in the most extended lifetime of the working electrode, paired with excellent sensitivity, is the 4-potential waveform. That's why we are using it basically as a standard, as a universal waveform for our applications. However, if you're aiming for the highest possible sensitivity, and if you accept that you might need to polish and exchange the electrode more often, then the middle option, the waveform 3P1, is suitable. But due to the high oxidative potential, cleaning potential, at 0.75 volt, it causes the highest wear, wearing down the gold electrode faster than the others. Still, as I mentioned, it offers the highest sensitivity, the lowest oxygen sensitivity, and very low drift in gradient runs. As I said, there is a trade-off. Then there is the traditional 3-potential waveform, 3P2, the best option for routine isocratic work with an oxidative cleaning potential of 0.6 volt, which causes moderate wear of the gold electrode. Now, when comparing the duration of the waveforms, you see 500 milliseconds for the 4-potential waveform and 1,000 milliseconds each for the 3-potential waveforms. Now, this is important to remember. You can require 2 data points per second, 500 millisecond and for the pulse. You can acquire 2 data points per second or 2 hertz with the 4-potential waveform, and only 1 hertz with the 3-potential waveforms. Essentially, the 4-potential waveform is especially useful for integrating early eluting and very sharp chromatographic peaks. And here's why we abbreviated the pulse sequences. It's easier to compare. The highest sensitivity is with 3P1, while the best long-term and peak area precision for early eluting carbohydrates is with 4P, with the 4-potential waveform. The baseline drift for sodium hydroxide and sodium acetate gradients is lowest with 3P1. Choosing triple pulse sequences means more electrode wear and more frequent polishing. Just please keep that in mind. That's why we suggest using the 4-potential waveform, by the way. Now, there's more. We do offer 2 cells, 2 amperometric cells. So the one is the flex cell, which is a thin layer cell, a thin layer design, and the sen cell, which is a wall jet design. The wall jet design directs the column effluent at a right angle to the gold electrode, increasing sensitivity. Using the flex cell, you'll use the flex cell if you'll often use different working electrode materials like silver, glassy carbon, or platinum. We also use different reference electrodes, the silver chloride, and the high ref, and I will have to explain what the high ref electrode is. And with the setup that we have, we can use these reference electrodes interchangeably with the same pulse sequence. Now, why is that? Because that's quite unusual. First, here you see a simple plot explaining why we can use the identical pulse sequences with both of the reference electrodes. We measure the potential difference between 2 identical cells, except of course for the reference, at different pH levels using the same eluent or depolarizing electrolyte solution. As you can see, the difference diminishes at higher pH values, indicating that the reference potential become identical at high pH. Therefore, and we are using high pH eluents for HPAEC-PAD, therefore we can use the same pull sequence. Now that we have clarified that, the question is, what makes the high ref electrode so special? The high ref electrode is a solid-state palladium electrode that requires no conditioning. It is maintenance-free and has a long lifetime, which is especially noteworthy these days. I mean, nobody has money to replace things. Now the question is, should I use a silver chloride reference or should I use the high ref electrode? Well, we strongly recommend choosing the high ref reference electrode for ease of use and cost savings. However, if your SOP or your recipe demands the use of a silver chloride electrode, well, use it. Unlike other commercial solutions where you often need to exchange the entire reference electrode, the only regular maintenance on our side is replacing the saturated potassium chloride solution. And this is done in a few minutes and it's quite cost effective. Now, there is something else to consider with a sense cell. What if the sense cell allowed continuous adjustment of the working cell volume without needing any spacer or gaskets? In this slide, you see the assembled sense cell and a small handle for adjusting the working cell volume by turning. This allows you to fine-tune the volume and consequently the sensitivity. In other words, the lower the cell volume, the higher the sensitivity, the larger the cell volume, the lower sensitivity. With thin layer designs, or for example our flex cell, we would need to exchange the spacers or gaskets as they are sometimes being called. But here all you need is a small tool to adjust the active working cell volume. And the plot on the right illustrates the effect of the working cell volume. So larger volumes, lower sensitivity, you see the current decreasing, and if we go to smaller volumes to the left, you see the oxidization current increasing. Just recently, we were involved in transferring the method from an older instrument to the state-of-the-art Alexis instrumentation. And during this process, the user found a way to avoid diluting many samples by simply adjusting the active cell volume to setting number 3, which is the largest cell volume or the lowest sensitivity. So while we couldn't prevent all dilutions, we significantly reduced the number of dilutions needed and minimized the dilution ratio for others. All in all, leading to higher overall method precision. Now, even with all these steps, there still might be the need to polish the working electrode. Now, let's have a look on how to polish a working electrode of a sense cell. Let's talk about how to polish a sense cell working electrode. First step, rinse the polishing pot. Dab off the excess water. One, two, three. Set the cell volume to the lowest setting 0. Start polishing the working electrode. Use a figure-8 motion. Well, any letter of the alphabet will do, but do it for about 1 minute. And polish the auxiliary electrode as well. Few dabs here. Take the cleaning pad. Polish the auxiliary electrode. Rinse off the diamond slurry. First with tap water. Then with deionized water. Dry the block. Reset the volume to the setting 3, the largest, and then to the setting that you want to use for your measurements. Squeeze some water through the ports of the electrode block, in case that some particles might have ended up there. Dry it. Clean the surface with an organic solvent like acetone. And don't forget to rinse the reusable pad. Tap water and now deionized water. Ready to go? Well, Yara, why don't you take over now?
Yes, thank you, Detlef. So far, we covered water quality, carbon dioxide and degassing, the eluent tray, and the preparation of sodium hydroxide and sodium acetate. We discussed the cell design, the waveform, and how to polish the electrode. Now it's time to talk a little about relations. Don't worry, correlations. It might come as a surprise, but did you know there's a correlation between ice consumption and shark attacks? No joke, there is. If you look at this plot, you will see a pretty strong correlation with an R-squared of 0.993. So the correlation is real. The implication? Obviously, we should consider reducing the amount of ice sold at beaches, right? It sounds funny, but you know what? This is the proper way to use the correlation coefficient. I will show you the original publication on the next slide. The correlation factor and its origin. That's the title of the slide. The correlation factor was designed to examine the possibility of a link between animal behavior and some environmental factors. The intention was to find correlation. Causation was then another exercise. And why is that important? And why do I bring that up concerning the question of how to improve the overall quality of the analytical results? Detlef?
Yep. Thank you, Yara. Yeah, we did talk about correlations, and this leads us to some hints on calibrations. So please be prepared for some surprises. And the surprise begins here. In 1998, the HPAEC published a document titled Guidelines for Calibration in Analytical Chemistry. It is a HPAEC recommendation, not just an article. It's a formal recommendation. Let me also bring up the page that is crucial to what we are discussing. The discussion focuses on the correlation factor. And reading through the yellowish part of the text, it says, the correlation factor, which is a measure of the relationship of two random variables, has no meaning in calibration under the condition mentioned above because the values x, the amount, are not random quantities in the calibration experiment. And then the correlation coefficient r can be meaningful for the relation between two random variables, shark attacks and ice, but should not be used in calibration. It makes sense because when we do a calibration, we do choose deliberately the amount of the calibration solution or the amount of the calibrant. Now, when I read that the first time, it did shock me. because it means that HPAEC does not recommend using the correlation factor anymore. And I don't know about you, but for most of my scientific career, I used R-square and the calibration relative standard deviation to judge the calibrations. So what now? So when we learned about the correlation factor, or the not use of the correlation factor, we looked for guidance. And using the right keywords, and there's 2 keywords on top of the screen at the moment, and your favorite browser, you will find excellent resources. And one I find specifically helpful is the website of the NELAC Institute. And on this website, you find recommendations and procedures supported by the EPA, the Environmental Protection Agency. The document in front of you is titled TNI1, Guidance on Instrument Calibration, and that is a valuable resource on available tools and potential processes. The U.S. Environmental Protection Agency and other organizations cover the process I'm talking about, and this document introduces the so-called RSE, and as a replacement, the RSE stands for relative standard error, as a replacement for the correlation factor and the RSD of calibration. Now, another shock. We had to learn that the calibration RSD is only defined for calibrations based on the average response factor. However, we are using the least square method to calculate our calibration functions. Bummer. So, and here comes the RSE into play. The relative standard error is a measure for the deviation of the measured calibration concentration against the expected value, and allows the comparison, and this is important, it allows the comparison of any calibration type, linear, quadratic, weighted, or unweighted. In other words, an independent tool to compare the performance of different calibration approaches during method evaluation, and then you decide on the calibration approach that is giving you the lowest RSE, which is the best match between experimental and expected data. Now, despite its high value, how do I use it and where do I find information? Well, let me show you something. First of all, if you are a user of MPower or Chromium, you belong to the lucky ones because RSE, the relative standard error, is included as a report variable or calibration variable in that software tool. Just look for RSE in the help page or the help function of each of the data systems and you will be guided through the process. But what if your data acquisition system does not give you RSE as an included variable? Are you left out? No. You just do your internet search and look for NELAC and RSE, and you will end up on the NELAC homepage, where you'll find an RSE calculation spreadsheet. Download the Excel file and follow the instructions. So now you have the RSE, but what do you do next? What are the next steps? Well, the process is pretty simple. It is simpler than I initially thought, and it works every single time. During the method validation, you apply different calibration models, linear, quadratic, with or without weighting. So 1 over x or 1 over x squared, 1 over amount, 1 over amount squared. And you apply that to your calibration data set. And all you then do is you choose the one with the lowest RSE. That's it. It's straightforward. Of course, depending on your SOP and quality assurance or quality control program, you will need to double check. But I can tell you from own experience that this was a big eye-opener. It explained why in my calibration curves, and I'm talking about myself, the deviations consistently increased with decreasing amounts. Since I follow the RSE concept, that has changed, and the quality of the data has significantly improved. Now, in order to demonstrate, I brought 2 plots with me, and both were derived from and with the same calibration experiment and data. We plotted the relative amount deviation to measure how close the calculated concentration is to the expected calibration. on the left-hand side, so here, you'll find the results of a linear calibration plot which is forced through the origin without any weighting. This is still the standard approach commonly used in many laboratories still today. If you follow the values from high concentrations to low concentrations, this direction, you will see that the deviation increases as the concentration decreases. But if you treat this data set, the same data set, with a quadratic calibration model, which you don't force through the origin, and apply a weighting of 1 over amount squared or 1 over x squared, look what happens with the relative amount deviation of each calibration level. We did not change the integration or manipulate the concentrations of the standards. We simply chose a different calibration model. Just a look at what it does to the relative amount deviation. Now, you see that the bullet points are close to the theoretically best possible value, 0. So guess which of the two models has a lower relative standard error, the left or the right one? The rhetorical question, the right one. And of course, you need to be curious, you need to be skeptical, and you need to check that this works for you. My recommendation, don't do extra experiments, don't do extra work. Use the data that is already existing on your computer, the data that you already have. Apply it to that evaluation. Use different calibration models and select the one that gives you the lowest RSEs. And if this leads to improved analytical figures of merit, which it should, only then consider changing your SOP. In my humble opinion, this is the easiest way to improve the quality of your analytical data, and all it costs are a few mouse clicks. Ladies and gentlemen, we approached the last part of today's presentation, the summary. So during our presentation, what did we cover? We covered that DI water is one of the most underestimated chemicals in the laboratory. We also discussed degassing the eluent with nitrogen, cost saver, using the eluent tray 210. Whenever possible, use the 50% sodium hydroxide solution weight to weight. And use the highest quality sodium acetate. We prefer the trihydrate because we use it with high success in our R&D facility in Alphen in the Netherlands. Ensure that all chemicals are of the highest quality. Then we continued talking about the best waveform and concluded that in most cases, the 4 potential waveform is the best choice. However, if you have specific needs regarding sensitivity or baseline drifts, then opt for one of the 2 other 3 potential waveforms. With that decision, however, you accept the increased wear of the electrode. So, which one is it? Select the best amperometric cell. By the way, we recommend the 4 potential waveform because it gives you the best of all worlds. Select the best amperometric cell. You have the choice. You can choose the flex cell or the sense cell. If you're looking for optimum performance, high sensitivity, maximum flexibility, and an adjustable cell volume, and you want to combine all of these with a solid-state palladium reference electrode, then sense cell is the right choice. However, if you need to follow a method or a recipe that describes a thin layer cell, then the flex cell would be your choice. Optimize your calibration model effectively. We discussed the RSE parameter as a way to interpret and compare calibration models. Just try it out. Remember, don't do extra work or measurements. Just use existing data and compare the results in the simplest way. RSE is a tool that does not affect the calibration itself, but it provides useful insights to guide your decision. Now I get it. That was a lot of information, though I hope you enjoyed it. So from our point of view, thank you very much for your attention.